So good morning, dears. This is my part 2. As it is, I have forgotten. The video about metallic character and melting point and atomic radii, ionic radii, etc. was already done, but then it was not found along with the uploaded videos. So I am making it separately. And one of the girls had messaged me that I had that the metallic character, melting point, and atomic radii was not mentioned. We had done a video, but it somehow got deleted and it was not uploaded. I'm sorry for that. And it shows your concern. It shows your attitude towards our classes and appreciate it. Okay. Now we pass on to the metallic character which we have left out. The atomic number goes up, down the group, the atomic number goes up, okay? It increases. So the atomic size increases. And what happens to the Z effective? Z effective means the attraction of the nucleus or the nucleus attraction, isn't it? So the nuclear attraction decreases. Why? Because the atomic size is keeping on increasing. So as a result, this is becoming less, that is Z effective decreases, and as a result the metallic character, that means the capacity for donation of electrons, so the electrons is pulled out, that is what we call as a metallic character. You know that very well, isn't it? So we have discussed it many a times in the class. So metallic character means it is losing of electrons, okay, and gaining a positive character. So that is what is mentioned here. So as one moves down from nitrogen to phosphorus to arsenic to antimony to bismuth. Now bismuth shows the maximum metallic character. So the same thing is applied here also. As you can see here, the Z effective decreases and the metallic character goes up, or the capacity to donate electrons increases. So as we move down the group, the metallic character increases. I hope you understood. Okay, now we pass into the metallic, the melting point. Okay, sorry, it's melting point, MP. So what happens? The melting point, as one is, the melting point is decreasing. Okay, in bismuth, you can see that it is having the maximum melting point. So in nitrogen, the melting point is minimum. See, minimum melting point because of its diatomic structure. Here we have a layered structure. What do you mean by this layered structure written here? That it has so many layers of orbitals. That's what is meant. Okay. See, we come up to the 6s2 and 6p3. 6p3 in the case of bismuth. So that is what is mentioned here. Okay, so that means the bond, the electrons are increasing. So to take out from those electrons, to leave off all those electrons from the periods, it takes a lot of energy. So that is why the melting point goes up. So the melting point increases as we go down the group. Okay, now atomic radii and in ionic radii, as you know, the atomic number goes up, the number of shells goes up. So the atomic radii increases, the ionic radii increases. So naturally the covalent radii too increases. That is what we mean by here telling that the atomic radii and ionic radii increases, means here they have the covalent character. As you know, they are non-metals. They have the covalent character, and so the covalent nature or the covalent radii also increase. So that is what we have missed out. So that I have explained to you. I hope it is clear enough for you. We are not in a position to go and take the video, so that is why this also is a way of explaining. If you have understood, you have to follow this up, write it in your notebook and keep. And we will be having a test, so that I know that you have understood. And if there is any doubt, like anything missed out, or you have some doubts in it, you have to send me private message. Then only I can rectify it. I hope you understood. Thank you. So we were in the chemical properties. I told you chemical properties, oxidation states, ionization, inert pair effect, inert pair effect, etc. we have discussed, isn't it? So we know that this is now we are talking of the chemical properties. So when we talk of the chemical properties, we have to first talk about the chemical the reaction with the hydrogen, because as you know, hydrogen is very abundant, isn't it? We have a hydrogen present in the atmosphere, so we have to deal with the reaction of nitrogen or phosphorus with hydrogen in order to explain the chemical properties. Okay, so let us understand the chemical property of hydrides. Usually we have to study in this particular chapter, we have to study about the hydrides, halides and oxides. Okay, so hydrides, suppose we are talking of hydrides, what will be the hydride formed? See, ammonia, that means NH3 and PH3, that is a phosphorus hydride. This is a nitrogen hydride. I hope you understood. So we'll be learning about the hydrides, okay, and halides, oxides, etc. in chemical properties, and some of the things which we are dealing will be along with ammonia, because ammonia itself we have to study in some detail. I told you about the Haber process and things. Okay. So we will be studying about this Haber process, and then how is the preparation of phosphine. All those things we will be learning in detail. But now in order to have a general idea about what are these hydrides, halides, oxides, okay, then only we will be able to explain the chemical properties in a particular detail. Okay, so the first thing that when a hydride is formed, so we are dealing with hydrides, we like the property, then down the group and the reason. I told you these are the ways by which questions will be asked. So hydrides, so when we talk about hydrides, you see here NH3, so nitrogen is 1s2, 2s2, 2p3. Okay, so it is 2p3. So 1s2, 2s2, 2p3. Okay, so here we have the bond will be there, that is the ammonia, that bond is there, nitrogen, hydrogen, 2 bonds, and then the distance is 107 degrees. Okay, and you have learnt this in 11th class too, about the pyramidal structure of ammonia. Why is it having a pyramidal structure? Actually it is sp3 hybridization. So what is hybridization here? It is sp3 hybridized, isn't it? But sp3 hybridization, that means this s orbital is partaking, and also this p orbital is also taking part, isn't it? So like that, sp3 hybridization is seen here. As for sp3 hybridization, usually the bond angle will be 104.5 degrees, isn't it? Because it will align in such a way that so that there is minimum repulsion between the bonding pairs. But here you see a lone pair of electron, isn't it? Nitrogen is having a lone pair of electrons. So there is lone pair, bond pair repulsion here. Okay. As a result, the bond angle gets reduced. Okay. So as a result, the lone pair repulsion, the bond angle becomes 107 degrees. Okay. So here you can see that ammonia is having a pyramidal structure. If you draw it like this, it will be a pyramidal kind of structure. Okay, so this ammonia. The same with phosphorus also. Phosphorus, 1 is 15, 1s2, 2s2, 2p6, 3s2, 3p3. I told you. So here also, you see that even then the bond angle is even more reduced here. 93.5 degrees only is there. Understood? So here we see that the bond angle is reduced. Here also the hybridization is sp3. Now we will try to explain as to why it is so. Okay, the bond angle, as one proceeds in the hydrides, so ammonia to phosphine, okay, to down under to nitrogen phosphorus arsenic hydride. Okay, then why does the bond angle become lesser and lesser? So that one such question would come. You know, it's a probability. The bond angle. Now atomic size of the central atom, what happens to the atomic size? Nitrogen, here nitrogen is smaller, but phosphorus is much bigger than nitrogen. Why? Because it has one more shell. You know that, isn't it? So now what happens is atomic size of the central atom increases. Okay. Now we have the chemical properties of hydrides itself continued. Okay. the thermal stability. These are the questions that are normally asked. That is why I have put it like this. So as the thermal stability, what happens to the thermal stability? Okay, it decreases down the group. That means the maximum stability is for NH3, then comes PH3, then ASH3, SBH3 and BiH3. Now we have to write the reason for that. Atomic size of the central atom increases, then what happens is that M and H stability decreases. That is the metal hydride, or you can write the element hydride. Okay, the element, the central atom, the element. Why is it not called a metal? Because it's basically a non-metal, isn't it? So I am putting it as EH. Okay, it's better that you learn it as an element. E represents the element and hydrogen. Okay, those EH bond, this bond, you know, if this is big enough, see, it's far away, isn't it? So that is what is happening. Okay, so EH stability decreases. That is, stability is inversely proportional to the size. So I hope you understood. So that is why we say that thermally stable is actually NH3. Less than that we have phosphine, then arsenic hydride, then antimony hydride, and then bismuth hydride. So usually this is asked. Okay, so you can give the reason as 2 points like this. It is when atomic size of the central atom increases, the EH, that means the element and hydrogen bond stability decreases, and as it is, stability is inversely proportional to the size of the central atom. Okay, so then the reducing character. What do you mean by reducing character? See, reducing character means it is easy to give away its hydrogen. Understood? So that is what. So the reducing character is increasing. I mean, increases. See, NH3 is having very less reducing character, whereas PH3 is having higher reducing character, and ASH3 is higher than that, SBH3 higher than that, and BiH3 higher than that. Why is it so? Because the atomic size increases, bond strength decreases. So easy to release hydrogen, isn't it? Bond strength decreases means the bond in hydrogen atoms can be released very easily. So its reducing character will increase. So which is having the strongest reducing agent? Which is the strongest reducing agent? That is the question that is normally asked. You will be definitely asked in the 1 mark question as to which is the strongest reducing agent, which hydride of the nitrogen family is having the highest reducing character, or you will be asked to comment on the reducing character of the hydrides of the nitrogen family. So this was asked last time. Okay, not this year, but last year this was a question. Comment on the reducing character of the hydrides of the nitrogen family. So you have to study this and keep, and this is how it is explained, and this is having the this is behaving as the strongest reducing agent, and NH3 is the weakest reducing agent. I hope you understood. Okay, now we can pass on to the next slide. Okay, so now the melting point, one important these are the hydrides. I told you hydrides continued. Okay, so we are talking of the melting point, or not of nitrogen, phosphorus and all. We are talking of the hydrides. Okay, so here we are continuing with the hydrides continued. Okay, so here we can see that the melting point, so you can see the melting point here, it decreases except for NH3. Okay, you have this table here. You can see the table here. I hope you can see it. Now, if you have to zoom in, you have to zoom in a little bit. Then you can see that here the melting point. Okay, you can take your book and see. I will try zooming in. I don't know whether it will zoom in. No, it's not. So you can see that the melting point there is X. Yeah, it's zooming in. See, you can see that it is. See, these type of tables are quite important for you. Okay, so you can see that the melting point here, you can see the melting point for ammonia. Ammonia is actually 195.2, and here you can see 139. Then it is keeping on increasing. 139, 156, 185, like that it is keeping on increasing. But you can see that here, see for NH3, why is it so that it is high? Here the boiling point is also high. Now how to explain this? Okay, so this one, how to explain this phenomenon? So there are certain things which are, you know, cryptic or hidden in your tables like this. Okay, the tables which are given in your textbook, certain informations are you know, you have to decipher from that. So we have to actually decipher such things. So why is it so that it is reducing, or why is it that it is increasing, like that we have to decipher. Now the general trend is that from pH3 to ASH3 to SBH3, it's keeping on increasing. Okay, you can see here it's keeping on increasing. Now except for this, why is this an exception? NH3 and 238.5 here, and you can see the boiling point and melting point. Why is it so high? Now that question is there. Did you understand? So here you can see that, you know, okay, let's zoom out a bit. Okay, you can see that the melting point here, okay, it decreases except for ammonia I have written. Now why is it so? Because ammonia shows hydrogen bonding. You can see that here. Okay, nitrogen is electronegative, so, and it is a small molecule, so it can form a hydrogen bond with the adjacent ammonia molecule. Okay, so can you see that now? Yes. So here you can see that this is having a bond, forming a bond, and this is what we call as a hydrogen bond. So because of this hydrogen bond, it is rather quite high for ammonia. But except for that, it is keeping on increasing. It shows the trend just like this as shown in the boiling point too. Okay. So now for pH3. So in the case of pH3, the atomic radii increases. For phosphorus, van der Waals forces increases. So the melting point and boiling point keeps on increasing. But in ammonia, it is exceptionally high. Why is it so? Because of hydrogen bonding. You have this question also here. These questions that are put in these boxes are quite important. Okay. So you can see it here. You see that pH3 has a, can you see that? I don't know whether I can zoom in. I will just try to zoom in. Yeah, you can see here. See, why are the pentahalides, I mean not that, pH has a lower, see, pH3 has lower boiling point than NH3. Why? Unlike NH3, pH3 molecules are not associated through hydrogen bonding in liquid state. This is why the boiling point of pH3 is lower than NH3. I hope you understood. Now, why is it that it is not forming hydrogen bonding? That we will study in detail in the coming classes. But I will give you a hint. Why is it so? Because nitrogen is a very small molecule. Okay, and it doesn't have any d orbital or anything for donating or taking in electrons or anything for any bond formation or anything. I hope you understood. So nitrogen is not okay. Now we pass on to the halides. Okay, nitrogen halides and phosphorus chlorides, like phosphorus pentachlorides and things. Okay, so let's see. Two types of halides are formed. You can see with the halides there are two types of halides formed for the nitrogen family. Okay, so what are the types? Trihalides. They are trihalides and pentahalides. Okay, so trihalides and pentahalides. Okay, so here we have as it is mentioned here, we have sp3 hybridization, and here we have sp3d hybridization. Okay, here also I have written as mx3, but in your book it is explained as ex3, where E is the element. Okay, element in question. That means it will be nitrogen, phosphorus, like that. Okay, so let us learn it like that only. Okay, in your textbook it is like that. So ex3, it is ex3 means it is a trihalide. That means it has three as valency, isn't it? Nitrogen means it has 3 valency. So in the same way, phosphorus also has 3 valency, isn't it? Phosphorus shows both the nitrogen, 3 and also 5. Okay, so let us see. here we can see that PCl, for X is actually fluorine, chlorine, bromine, iodine, like that. So how are the halides formed? NF3, NCl3, then you put Br here, NBr3, then Ni3, like that. These are trihalides of nitrogen. Once more, trihalides of nitrogen. Okay. Now this will show sp3 hybridization, and as I have explained, a trigonal pyramidal shape only. Okay, NCl3, you can see here the two lone pairs are here and the chlorine atoms will be arranged like this. The same thing, 1s2, 2s2, 2p3, and the hybridization is sp3 and the chlorine atoms come here this side. Understood? So that is how the NCl3 is formed. NF3, NCl3, NBr3, like that. These are trihalides. I hope you understood. Okay, now we move on to the pentahalides. Here you can see the pentahalides. Okay, the pentahalides, they have trigonal bipyramidal structure, sp3, and EX5. You have studied this. I mean PCl5. I am not talking of NCl5. I am talking of PCl5. Let's take for example PCl5. I'll tell you why, the reason it is, like, you know, I'm talking like that. But PCl5 is of interest to us. Okay, here also you can see PCl3 being formed. Okay, so in the same way as NCl3, here PCl5 has a special structure, isn't it? So it has a trigonal bipyramidal structure. That means these chlorine atoms, 3 equatorial bonds are there along the equator. You can draw it to this side also. Okay, in your textbook maybe it is drawn to this side. That also is fine. Okay, this also is fine, but it should be on one plane, plane, that is equator. Just as we say that, you know, like this, it is in one equator like this. Okay, that means, and the bond above and one bond is below this, so like that. Okay, so along the equator it is. Okay, so equatorial plane, this is equatorial plane, 3 equatorial bonds are there and 2 axial bonds. That means up and down, one chlorine here, one chlorine here. Now, what is the peculiarity of this? Equatorial, equatorial all are of the same length. Okay, the bond length here is just the same, and the axial bond, that is 202 pm. Okay, picometer, and then here up and down it is 240 pm. That means it is a little longer. The axial bonds a little longer than the equatorial bonds. Okay, you have questions based on that, isn't it? I think you have had questions, or you will be learning more about it. Okay, now this one, it is why is it so? Because they suffer more repulsion than the equatorial bonds. Here the repulsion is more than the equatorial bonds. So as a result, this bond length is more. I mean this one, 240 pm. Here also it's 240 pm, and along the equator, this bond and this bond is only 202 pm. So these are the basic things that we have to know about a halide. So we will be learning in detail about all these things. If in particular we want to have some particular reactions, so PCl5 and all, we have particular reactions based on this one. So then, okay, so here we have a question. This is how the question will be asked. Compare the stability of the trihalides of nitrogen. Okay, the trihalides, the general formula I have given here. Also I have to make it as EX3, isn't it? Okay, EX3, then it can be fluorine, then it will be NF3. Okay, so nitrogen, fluorine. Okay, nitrogen and fluorine, nitrogen and chlorine, nitrogen and bromine, nitrogen and iodine. Like that we have made the trihalides of nitrogen to test and compare the stability of the trihalides of nitrogen. Now this is the question. Compare the stability of the trihalides of nitrogen. Now nitrogen, it's common. You know that nitrogen is all common here. Now we have to put fluorine 3 atoms here. Now chlorine 3 atoms here, bromine and iodine. Then only we can compare the stability of the trihalides, isn't it? Because we are basically talking about the trihalides of nitrogen. Okay. So as we go down the group, what happens? The size difference between the NX increases, isn't it? The size difference. See, this nitrogen remains the same. Here also nitrogen, here also nitrogen. It's a small molecule. But here you see this is F3. Okay, so fluorine, then chlorine, then bromine, iodine. You know that when it comes to iodine, it's a very big atom. It's a very big molecule, isn't it? So the Ni3 becomes a very big molecule because of the size of the atom of size of the iodine atom. Understood? So as you go down the group, the size difference between NX increases. As the size increases, the NX3 bond becomes less stable. Okay, NF3 is most stable because less electronegativity difference between N and F, and the stronger bond will be formed. So lesser the electronegativity differences, stronger will be the bond. So which is the most stable? We can say that NF3 is the most stable. So this is the most stable. Most stable among the trihalides of nitrogen. Okay, and this will be the least stable. I hope you understood. Okay, so these are normal questions. Okay, so as we work up the group, then we will know as to what are the questions basically asked from this, and then we will arrive at conclusions. I hope you understood here this one. Okay, compare the stability of the trihalides of nitrogen. So this is the answer to that. Okay, go through this, write this down, put this particular box, then write most stable here, least stable here, and study it well. Okay, now we pass into the next slide, that is why is NF3 okay least basic, okay, and it is less basic than Ni3. Okay, so which is the most basic? Ni3. And which is the least basic? NF3. Okay, now we are trying to explain it. Okay, you will be asked as to which is least basic, or according to the basicity you have to arrange them. Okay, so I have arranged it here. So NF3 is least basic than Ni3. Okay, is less basic than Ni3. Actually, it should be written like that, isn't it? Less basic. But then we we have to make a point that it is least basic too. Okay, you can make it less basic. It's okay. So here, see, according to Lewis concept, you know, Lewis base. Okay, you can say Lewis base or Lewis base, whatever. Lewis base easily donates electrons, isn't it? So NH3 also, it is a Lewis base, so easily donate the electrons. So that is one concept of Lewis acid and base concept. So based on that concept, it can easily donate its electron. Now consider this case where NF3 is there. I have drawn it here. Now F is highly electronegative and it pulls the electrons to itself. I hope you understood. Now the electrons on the nitrogen becomes less available, and as a result the nitrogen thus cannot donate electrons, hence it is least basic. I hope you understood. So what is happening? Here it is small molecule. Fluorine is very small and it is very highly electronegative. So as one proceeds to chlorine, bromine, iodine, etc., the atoms attached to it is big enough and it is not able to hold on to the nitrogen's electrons as much as we see in NF3. So as a result, the bases, the behavior of it as a base decreases as one goes from nitrogen fluoride to nitrogen iodide. I hope you understood. Okay. Now let us see how it is to be explained. Fluorine is highly electronegative, so it pulls the electrons like this. Okay, so it's pulling the electrons. So is the electrons available to be donated? No, it's not available for donation, isn't it? It is not available for donation. So what happens is that it will actually behave less as a base, or it is least basic in nature. Now there is another framing of question here. Why is PF3 more acidic among all the trihalides? The same question can apply here also. When it is least basic, it is most acidic. I hope you understood. Okay. Now how to describe it in the acidic sense? Okay. So we have taken another example, that is all PF3, more acidic among all trihalides. Now PF3 is more acidic here. See, and this is the least acidic. So this is the most acidic here. Understood? Why is it electron pair acceptor? Means Lewis acid means electron pair acceptor. See, P has vacant d orbitals. P has vacant d orbitals here. Here also it has vacant d orbitals. But see, F has higher electronegativity and accepts electron easily. So it's more acidic. I hope you understood. Okay. And here it is electron withdrawing. Iodine has less electronegativity, electron withdrawing capacity, and accepts electrons and is low. That is least acidic. So learn this properly, then only you will be able to understand it. Okay. Now I'm going on to the next slide. Now this is the usual concept that is being asked. Okay. And this also might pop up. So you have to explain it. You have to study both these things. Okay, so there is one important question put in your 162, page number 162. 7.1. Why are pentahalides more covalent than trihalides? So here you can see the oxidation state of +5 in pentahalides is more as compared to +3 oxidation state in trihalides, as it is 5 and this is 3. Okay, both are positive. Now, due to the high positive oxidation state of the central atom in the pentahalides, these atoms have larger polarizing power than the halogen atom attached to them. So, in the case of trihalides, due to +3 oxidation state, the central atom will polarize the halogen atom to a lesser extent. And when it is +5, it will polarize to a larger extent. Hence, the pentahalides are more covalent than trihalides. What do you mean by covalent character? Covalent character means it is sharing of electrons. So sharing of electrons. Okay. So in trihalides, it doesn't have much of a covalent character. I mean, it will be less, isn't it? The pentahalides will have more of a covalent character. Now, why is it so? That sharing is more. Why? Because of the polarization of the more polarizing power of the +5 oxidation state. Okay. Okay. Now you learn that and you have to put this question in your notebook and learn it. This is the reason. Now, and one more thing, as examples, here there are certain questions given here. Example 7.1, example 7.2. Okay, all those questions I need in the notebook. And 7.1 in text question, I have answered that question you have to put. Why is BiH3 the strongest reducing agent among all the hydrides of the group 15 elements? That question is also there. So all that you have to put in your notebook. You can see it here. I hope you got it. Yeah, this one. These questions. This example 1, 7.1, 7.2, 7.1 and 7.2 question in text questions. I want it written down in your notebook. Okay, that's homework for you. Okay girls, I thought of taking this as a separate session, but it is very small, so I'm taking it along with this because we are talking of the oxides. Okay, oxides are of two types, the same, trioxides and pentoxides. Among the oxides of group 15, which is more acidic, that is the question that usually pops up from this particular part. Okay, now let us try to study about, have a bigger understanding and more understanding of the concepts like trioxides and pentaoxides. See, the trioxides +3 oxidation state because it can give away these 3 electrons and form a bond. Okay, now these 3 electrons +3, so it is N and O we write, and then we put nitrogen 3, oxygen 2, phosphorus 3, oxygen 2, arsenic 3, oxygen 2, antimony 3, oxygen 2, bismuth 3, oxygen 2. So these are all trioxides. What are they? Trioxides. Okay. Now, as we know, the non-metallic character, see here the non-metallic character, that is the, non-metallic character will decrease down the group. And as it is, we get the metallic oxide here, isn't it? More metallic. I mean, this is not a metallic oxide, but then we can actually tell that it is a metallic oxide. Why? Because as we proceed from top to bottom, the nitrogen is more a non-metal than bismuth. Bismuth is more of a metallic, is showing more of a metallic character. See, the metallic character decreases as one goes from top to bottom. And you know that the non-metals form usually acidic oxides. I hope you have not forgotten. The basic oxides are formed by the metals, and these are non-metals. Nitrogen is a non-metal, phosphorus is a non-metal, so they form acidic oxides. So if you are asked a question as to arrange these trioxides in their increasing order of decreasing order of acidity, how do you put it? Which will be the most acidic oxide? This one, isn't it? Naturally. So N2O3 is acidic oxide, and as we proceed down and down to the bismuth oxide, bismuth trioxide will be the metallic oxide here. So it will be basic in nature. Okay. So that is how we have explained. And let us consider the order of pentaoxide acidity. That too is just the same. N2O5, we have how to write that pentaoxide. I have put it here. See, nitrogen is having a valency of 5. So we put 5 here. Oxygen is again 2. Phosphorus has 5 valency. See, plus 5 oxidation state. Oxygen has 2 valency. Phosphorus has 5 valency. So it becomes P2O5. Arsenic 5, oxygen 2, As2O5. Sb5O2, so Sb2O5. Bismuth 5, oxygen 2, so it is oxide 2, so that is bismuth oxide is, pentaoxide is Bi2O5. I hope you understood how to write the formula. Now this formulas once written, now they will be asking you the order of the acidity. As I told you, here also the non-metallic character will keep on decreasing and the metallic character increases, and so as a result this will be more acidic, more an acidic oxide than this one. So this will be more acidic oxide and this will be a basic oxide. So what happens to the acidity? Acidity will decrease as one goes with the oxides or pentaoxides from top to bottom. N2O5 greater than P2O5 greater than As2O5 greater than Sb2O5 and bismuth oxide. So which is having having more acidity, or which is more acidic oxide? This one is more acidic oxide. This one is more a basic oxide. You just remember the metallic character, then you will be able to explain it very easily. Okay, now you understood. Now you have all the answers to the questions therein, the in-text questions. Then you have certain other informations too, and if you can study it properly, then the information that you have got or the concept you have got pakka. Okay, so now I will pass on to the next slide. That is, let me try to prepare it. That is, it will take perhaps a day. So until this you have to learn and write all these notes and keep, and then any doubts you can message me personally. As it is not very difficult to understand these concepts once you understand the reason behind it. I don't think it will be a problem for you to understand the concepts perfectly well. If you can't understand it, again and again you can rewind in here and then make notes accordingly,